All right, let's get started. Hey, everybody. Yeah, welcome. Last talk of the day, right? All right. Well, yeah. So let's make it count. All right, my name is David Borel, and I'm a manager on our SDK team. And my team focuses on the developer experience. So we do the engine integrations for Unity and Unreal. We work closely with Epic and Unity on those. And then we also build developer tools, the documentation, the developer website, and basically own the experience end-to-end to try to help you maximize the quantity and quality of apps in our store. As you know, the Oculus Quest is a new standalone headset, and it's going to give you the opportunity to address a very large market. But it's also, running on a different hardware stack than you're used to with, say, Rift development. And this talk will focus on some of the similarities and some of the differences between those two platforms. So we'll start off talking about the perceptual psychology that leads to presence. Who here is a Rift developer? OK, yeah, a good number of you. All right. So the Rift concept of presence is something we've talked a lot about. If you've ever attended one of my talks before, I've gone into details that we'll kind of skip quickly over here. But they also apply to Quest. But we'll also go into details on the differences between the two platforms. As you know, the Go is a very, very different development target from the Rift, and you can imagine how that also translates to Quest development. We'll talk about some of the things that our SDK does for you to help you hit frame rate and maximize immersion. And then at the end, we'll talk about performance optimization that you can do in your app and how to understand where the resources on the system are going. This, in many cases, becomes the dominant difference between the two platforms, and all with the goal of you shipping a really high-grossing, sticky app. We'll have Q&A at the end, but we're probably going to fill up the whole time slot. So please just meet us outside, and you can ask us any questions. And you can also follow up with us in the forums. So first, let's talk about 6 degrees of freedom presence. So who here has used the Go, targeted the Go in development? OK. Yeah, so as you know, the 3 degrees of freedom you get there are rotation about the x, y, and z axes. And then we infer a little bit of translation or positional movement based on that using kind of anatomical models that have been averaged over the population. That gives a pretty good sense of motion parallax, but nowhere near as good as what you can get from directly tracking the head's position. So on Quest, you now have the inside-out tracking system directly giving you that information, just like we do on Rift, with similar levels of precision and latency. So a lot of perceptual psychology research has been done around the sense of depth and the sense of spatial understanding. And they found that both binocular disparity and motion parallax contribute heavily to that. So as a result, your users will feel like what they're looking at has a stronger intuition. They'll have a stronger spatial understanding of the content. And here we have a pretty cool RGB plus D cap that has been displaced with 60 off tracking. So really cool things are possible not only with gaming but also with media with 6 degrees of freedom. But as Hugo described, Quest is going to enable you to do a lot of the things we currently do on Rift in a broader setting. So that's what we'll be focusing on for this talk. So let's talk about a couple of other perceptual cues that contribute to presence. One of them is vergence. So vergence is when your eyes angle in differently for different depths. So if you put your finger close to your face, your eyes are going to cross more. And if you move it far away off to the horizon, they end up looking almost parallel. And that's the dominant way that the SDK shows depth on the headset. We perturbed the image based on your eye offsets to show different images to each eye. And that's why stereo rendering makes things look closer or further away. What we don't do is change the accommodation of the image. So accommodation is a cue based on focus. If you move if you even close one of your eyes and move your finger closer or further from your face, you'll find that the background gets blurry, and you can still tell roughly how far away your finger is based on that cue. And we don't do anything there. So you need to be conscious of that when developing an app. Putting content less than 0.5 meters from the user's face may cause a little bit of blurriness or cross-eyed feeling, which is probably a good idea to avoid. People who have developed for Rift already know this. And it just applies because you now have touch controllers on the Quest device, and you have the 6-degree of freedom tracking. So these are things you may not have had to worry too much about developing for Go or Gear VR. Another thing we brought over is Guardian. So as with Rift, you have an initial setup stage when the user sets up the device where they trace a boundary. And if they get close to that boundary at runtime, it'll show up and improve their situational awareness and sense of comfort and safety. And as with the touch controllers that you know and love from Rift, we have haptics with the exact same API. By the way, Guardian has the same API. So the haptics API can use steady state vibration, and you can, for example, change the amplitude and frequency of that vibration each frame. Or you can just pass a waveform directly to it, and it'll play very precise haptic effects. So you can do things like reach out and pet the dog, or feel haptic textures on things like corduroy or whatever. So a lot of people have done creative things with this, but I still think there's a lot of room for innovation, and we're excited to see what you build with that. Now, I'd like to welcome to the stage Nick Whiting of Epic Games. Nick leads the XR development at Epic and is also leading the OpenXR development at Kronos. Thank you, Nick.
Hey, everybody. Wanted to come here to talk to you today a little bit about what it's like to make the transition from developing on the Rift to developing on the Quest, which I still have to continually to remind myself it's called the Quest now. So if I slip up, please forgive me. Sorry, Oculus. But the good news is that the Oculus SDK team has done a tremendous job making sure that the SDK and features that are exposed and that we're very used to on the Rift also work very well on the Quest itself. So you'll find that in terms of actually designing the experience, what it means to interact, what it means to use haptics, how to control the camera, and those sorts of things translate very one-to-one from the Rift onto the Quest. In fact, at Epic, when we do development on the Quest, when the designers are kind of iterating, in order to speed up the process, we develop on the Rift as kind of an analog for developing on the Quest, because you can be in the Unreal editor, you can change the scripts, you can change the levels, you can change behavior, and then you can click the play in editor button and get kind of an instant run of the game without having to worry about anything. So there are some differences because you are developing for Android. Unreal has made a lot of strides lately, largely in thanks to shipping Fortnite on mobile consoles to improve the Android workflow. So we've recently gone from Ant to Gradle, which has greatly improved our build and packaging times. But aside from that, hopefully it's very easy for you guys to get up and running with Quest, especially if you've done any work with Oculus Go. So let's dive in a little bit more specifically. So as I mentioned, the engines kind of do a lot of the hard work for you. So as you're developing stuff, the way you set up your camera, the way you set up motion controller components, the way you set up haptics, all that's exactly the same. So if it works on the Rift, it's going to work on the Santa Cruz when you develop it. But when you're ready to go actually test it on the Quest. I caught myself at least. When you're ready to go test on the Quest, there's just a few steps that you need to do. So first of all, you need to install the Oculus runtime and UE4. That should be pretty easy to do. Hopefully, you can all get that far. Next up, if I can click the button, there we go. Open the project. One thing I will mention at this stage, your project can come over directly from Rift and work on mobile. But one of the things that's useful, if you haven't done it already with your current Rift projects, is to make sure that you use the mobile presets for the template when you create a new project, and then make sure that you choose the scalable option. And that will basically turn off a lot of the high-end rendering features that won't necessarily translate very well to the Quest on a mobile chipset compared to the kind of beefier CPU and GPU on a PC. Next up, you need to enable VR. So the Oculus plugin is enabled by default in Unreal Engine, but it's good to go in and check there. One thing I want to point out, though, is the nice thing is in Unreal, the Oculus plugin is the same plugin for both the Rift and the Quest, so you don't need to worry too much about the differences there. You do need to make sure that you've installed the Android toolchain. And in Unreal, there's a folder in your Engine Extras folder that contains an installer. So once you install that, you should start to see options in the editor that let you package for Android. And up last, click Click harder. There we go. Once that's done, you can just go up to File, Package Project on Android. Then you can choose any of those texture formats that you like. Most people we found use the ASTC for performance reasons, but you can really select anything that's supported there. And then after that's done, it'll make a package. You can double-click to deploy it, and you should be good to go. So the big difference, since your application is pretty much created and controlled the same way, is the performance. So you got to remember that the Quest is about 5 to 10 times slower in terms of CPU and GPU than what you're used to working on the Rift. So a lot of your time kind of going from the Rift to the Quest device will be in performance and optimization. So I wanted to go through a few of the kind of high-level commands that people use, that we usually use for kind of gross-level debugging and performance. You put it on the device. If you're not making frame rate, here's kind of our step-by-step. The first kind of most useful command is stat unit, and that basically gives you 2 times how much CPU are you using and how much GPU time are you using. And that's really answering the question, am I CPU bound? Do I need to work on CPU performance, or am I GPU bound? At the beginning, you might be bound by both, and you just have to pick one or the other to start with. But this will kind of help you notice if you're not making frame rate, is it your CPU that's holding you back, or is it taking too much time on the GPU itself? Once you get through that, if you notice that you're CPU bound as opposed to GPU bound, one thing that you can do that's very useful, it seems very simple, but we use this a lot on Robo Recall, was to just pause the game using the pause command. And what that does is it shuts down most of the processing that's happening on the game thread, so things like collisions or any animation graphs that are ticking just go away. And what this lets you diagnose is that whether or not that what you're seeing that's eating up your CPU time is a gameplay problem that you can optimize in gameplay code or by simplifying your physics or your animation, or is it something that's on the render thread? And that usually indicates that you have too many draw calls or you're doing something that's requiring a readback from the GPU. Next step on that, if you find that you're GPU bound, or even in some cases if you're render thread bound, you can use the show command, and that lets you turn on and off certain features. So if you notice you're GPU bound, what you can do is, as a first step, say show post-processing. That will toggle on and off the post-processing path, and you can see how far the GPU numbers drop. So that kind of gives you an upper bound. Even if you were able to perfectly optimize post-processing, that gives you an upper bound of how much that you can actually save. And that lets you kind of target where do you want to hit first. You can do a few different other options like turn off animations, turn off skeletal meshes, turn off lighting. All those things kind of tell you, even if you're to do a perfect job, how much can you actually save? And that helps you kind of triage where you want to attack first. If you dig in deeper and find out a particular system is a little bit hot on your time, you can actually use the stat commands with a bunch of those features. One of the most useful ones that we've found, at least most developers, is stat physics, because if you're using destruction, cloth, or performance, or having too many collisions, stat physics will show you how much time each kind of bucketed physics task will take. So that lets you get a little more targeted on whether you need to simplify your geometry, simplify your collision, reduce the number of components in your scene. All those sorts of things can be gotten from stat physics. Stat anim is another one that tends to get pretty hot. A lot of people, animation is cool. Animation is what makes things feel like they're present and lifelike, but animation is also not free. So if you have a very complicated rig or a lot of blend shapes, a lot of times looking at stat anim to see which meshes are particularly hot or if there's something that can be done to optimize those will kind of guide you in the right direction. Stat scene rendering is another one. If you notice that the rendering thread time is still pretty expensive, so you pause the game and you're still using a lot of CPU time, stat scene rendering will let you do a quick check of your draw calls. I would say 7 to 8 times out of 10. I'm not willing to go 9 times out of 10. Too many draw calls are in your scene. And what that means is you have too many objects that are actually trying to be drawn at the same time. So ways to get around that is combining things in meshes or use mesh instancing in order to take things that you have to draw multiple times and combine them into one draw call. One command that is actually a little bit obscure in the engine, but is actually extremely useful, is stat dump hitches. So in your ini file, you can set a hitch threshold for a certain number of milliseconds, and then if the game hitches, if your frame takes over that threshold, it will actually dump out a log with all your timings. So this is really useful, especially if you have QA or play testers going through. If you set that dump hitch threshold, anytime that they hitch in the game, you can actually take that dump and then go look for what actually was slowing you down on there. So we use that a lot for the kind of the last minute stuff. It also helps, especially one of the things that causes hitches in VR we've noticed is spawning. thing. So you create an object, you create an actor. There's a lot of initialization code that comes along with that. Stat dump hinges can let you know if somebody's added something that's spawning in that you didn't actually know about previously. So it's a good tool to catch sometimes artists going a little too liberal with how many things they're putting in the scene. And then kind of a final piece of advice, if you notice that the GPU time is too high, if you saw Remy's talk yesterday about using RenderDoc, we got a lot of mileage out of finding scenes that were slow, and then stepping through the commands in RenderDoc. And you oftentimes see that, oh, there's a light here that's taking a lot of time to draw, but it's not actually contributing much to the end visual result. So we spend a lot of time going over RenderDoc captures of slow areas and trying to find, is there a way that we can do this that's a little bit cheaper for the mobile platform that still gets the same kind of visual effect? So with that, I'm going to turn it over to Jian, who's going to talk about the SDK. Thank you.
Thank you, Nick. So hi, everyone. My name is Jian. I'm a software engineer from Oculus. So I'm going to introduce our Oculus Quest SDK features. So since we own the whole stack of software and hardware, you can see a lot of features actually perform better than before. So generally speaking, our SDK handles everything from tracking your head movement to display the image into the headset. This at least involved tracking, optical correction, and latency correction. Also, we have a lot of performance optimization features inside the SDK, and we are experimenting more. So Oculus Quest uses 4 ultra-high FOV sensors to do 6 of inside-out tracking. So it also uses the same camera to tracking the 2 controllers. We optimize the tracking volume to make it as large as possible. However, there are still some dead corners. For example, if you put your controller behind your body, your controller may lose tracking. So as a developer, you should always design the app with the tracking volume in mind. So like Gear VR and Oculus Go, our SDK also does optical correction. The image would be distorted after the lens system. And for fixing these issues, we pre-distort the image in an opposite way. So the 2 distortions will cancel each other. Then the user can see an undistorted world. And the chromatic aberration is another artifact of the lens system. So different color of the light have different refraction angles. So it can introduce some kind of rainbow-like artifacts at the object's edge. So previously, we do this correction in our GPU by a piece of shader. But it needs a lot of GPU resource. So we let developers to choose use it or not. It's optional. So like Carmack mentioned in this morning's keynote, right now we have a feature we call hardware chromatic aberration correction. It doesn't use GPU at all. So potentially, we can enable all the apps with this feature. We can maybe see a huge impact on app quality improvement. And on Oculus Go, we have a feature called dynamic clocking. So now we bring the feature into Oculus Quest as well. So dynamic clocking can adjust the GPU and CPU levels according to the app's workload dynamically. So the device can choose save power when possible or work harder for avoiding missing a frame. Oculus Rift, we support asymmetric FOV. Now, our Oculus Quest SDK is supported as well. This allows us to use the eye texture resolution more efficiently. Means we render the same amount of pixels, we can achieve better visual quality. This is mostly transparency to developers. However, if you use screen space coordination in your shaders, you need to know the projection center is not the same with the eye texture center anymore. We have a blog post on our website to talk about more detail there. You can check it out later. We also have a fixed forwarded rendering in Oculus Quest SDK as well. So which let your application to render more pixels towards the center of the view. So this allows higher quality or better GPU performance. Depending on your app's detail or the content, you can choose to use low, medium, or high forwarded level. Here is an example how you can control those parameters in Unreal 4 Engine Blueprint. You can also change forwarded level at the runtime in any frame. Like we mentioned earlier, so since Oculus Quest supports asymmetric FOV, so right now we adjust the resolution distribution of the fixed forwarded rendering, so it's asymmetric as well. Another part, our time warp is still a key component of the SDK, which was designed for latency correction. As some people already know, so rendering a frame takes time. When we render a frame, your camera may look at one direction, but when displaying, your camera may look at another direction. So time warp can kick in here, shift the image a little bit to make it work better for a new camera direction. In practical, we do this asynchronously, which means no matter how fast your app running or how slow it's rendering, time warp will be kicked in at a fixed frame rate. If your app misses a frame, time warp will just reproject the previous render frame again to make the whole experience much smoother. So time warp works really well on 3DOF headsets like Oculus Go, since there are only rotational movements involved, mostly. So let's take a deeper look. For example, we have a camera look at the object as one direction. When we display the image, the new camera may look at a slightly different direction. We can try to find the relationship between the view direction and the rendered pixel. We find it's actually a fixed relationship. It doesn't matter how far the object is. That's why time warp can work well without knowing what kind of content is rendered. However, for 6DOF tracking, this is more complex. We can use the same example here. We look at one direction, but when we display it, it's not only look at another direction, it's also looking from a different location. If we are trying to find the relationship between view direction and the pixel, we will find this is actually dependent on how far the object is. That's to say, if the object moves far away, you need to find the pixel at a different image location. So if we want to reproject the pixel correctly, we have to take the pixel's camera distance into account. So we are doing some experiment to use depth buffer from app side to help this. We ask the app to provide depth information when submit a frame. Then our compositor can use the information to improve the reprojection. And some people may already realize, depending on depth buffer, that has its own limitations. For example, for transparent object, it's not so easy to get the depth value. So we can use the background depth, but the final quality may not as good as the opaque shader. And if your app's FPS is too low, the animation itself may judder. So reprojection can help smooth out your head movement, but it won't be able to help the animation judder itself. OK, so next, let me hand over to David to continue to talk about the performance. Thank you.
Me again. OK, so now that you know how the SDK helps you, let's talk about how you can actually optimize your own app once you've done all the things Nick described and found a bottleneck. So as you're developing, as Nick mentioned, it's very efficient to iterate with play and editor on Rift. How many folks here have both a Rift and plan to have a Quest? OK, yeah, so obviously if you already are developing for Rift and you're attending a talk about porting to Quest, odds are good. But you can use them together. Rift can often emulate the experience that the user will have on Quest, with the exception of some of those tracking blind areas and the size of the playable area, for example. In many cases, the exact same user experience can be had, and you can instantly see what that'll be like by pushing play. And so you want to leverage that while also having a reasonable understanding of the performance implications. So a good heuristic to use is to target a 20% utilization. So you can use the dump hitches command and set maybe 2 milliseconds as the hitch threshold. You can also watch in Unreal in the UFE, the front end, and make sure that CPU and GPU utilization are hovering below 20%. But how does that really work? So we'll talk in a moment about how to actually use the Unreal Profiler and then also some other tools that we have available. Note that no matter how much you optimize, there's always more power to be saved on the device. And if you can get down to CPU and GPU levels 0, you will actually extend the runtime of your app and basically make your app stickier. So we've done that with our Netflix app, and we've found that it can run for hours. But if you have to run at a higher CPU or GPU level, you're going to burn the battery down much faster. And if you're above 1 or 2, you might want to focus on that, even if you're hitting frame rate. As Nick mentioned, draw calls and geometric complexity in general contribute a lot to your performance cost. So the tiled architecture of most mobile GPUs, which we do use in our standalone headsets, duplicates some of the per draw call work across all the different visible parts of the screen. So if you have a single complex mesh that's spanning multiple tiles, that draw call will incur multiplied cost. So try to keep your meshes either isolated to screen regions or optimize the windings and optimize your meshes for locality. And also minimize the number of draw calls and aggressively use occlusion culling and other forms of culling to get rid of as much geometry as you can. Using simple shaders, in many cases, the best you can do on a standalone headset is to do a simple lookup shader, but you can actually get a lot of BRDF-like effects using atlasing. Just try to avoid the really expensive or really complex shaders that have dozens of ALU instructions and many texture lookups. Multi-threaded rendering is a new feature in UE4, but you can now pipeline work on the render thread and the RHI thread, so that'll help you save some of your CPU footprint. So in general, simplify, simplify, simplify. The less texture, geometry, and shader complexity your app has, the less work the CPU and the GPU will have to do. And you can also focus especially on content that's less visible. Stuff that's far away can often be rendered with a shader that's just a simple lookup, whereas if you have an ice effect that depends heavily on parallax, maybe that's only necessary for extreme foreground content or stuff central in the view. And UE4 has a very good LOD system. You can use level of detail to select which levels are visible at which times. So be sure to use them. Also, trilinear filtering. I think we've come a long way since last year. If anybody attended CarMax app reviews, many of the apps were not using MIP maps. So this year they seem to be. That's a good thing. But MIP maps are image pyramids. I think a lot of us here may be familiar with them, but I'll explain briefly for those who don't. It decimates the image successively so that when you look at it from a grazing angle or far away, meaning the screen coverage of the texels is relatively small, then it uses a simplified version of the texture. And that not only improves the numerical accuracy, it averages the texel values over the pixel that touches more than one texel. It also uses a smaller working set within the texture, reducing bandwidth cost. So it'll help you both with quality and performance. So strongly encourage. It's very easy to enable. GPU will compute the mip-maps for you. All you have to do is enable trilinear filtering. Simplifying meshes and shaders, you can have fallbacks that pop in when the LOD is reduced. So using those techniques, here's an example of what you can expect. On the left, we have a 700,000 polygon scene on the Rift. And on the right, we have a 75,000 polygon scene on the Quest. And Gabor Zauer gave an excellent talk earlier yesterday, going into a great deal of detail on how the trade-offs work there. Not all draw calls are created equal, but in general, the less draw calls you have, the better. We're recommending certain numbers of draw calls for Quest. But that doesn't mean that that's always a hard and fast value. Depends heavily on how many state switches you have, how much locality there is in terms of the shading and texturing. Anyway, the scene on the right has kind of the same aesthetic as the one on the left, and as a result, like when you play, who here has done the Dead and Buried demo on Quest? Okay, you're running out of time. In fact, you may be already out, but it's very much the same experience that you get on Rift. The feeling is very similar, and the team did a great amount of optimization to get that running on Quest. But I think it is a demonstration of what's possible. So here they are in motion, both Rift on the left and Quest on the right. Yeah, our Avatar SDK works on the Quest, and it's also possible to use custom hands. I think sticking the pinky out was not necessarily due to the headset. Okay, so UE4, as Nick mentioned, has a lot of helpful tools built in. In particular, the stat unit view and the profiler will give you a lot of the information you need to isolate things that are causing you to miss frame rate. So here's the UFE, the UE4 front end, and it'll show you a graph of the CPU and GPU utilization and allow you to break it down based on functional areas of the engine that are costing you the most. And as Nick mentioned, you can turn off and on different parts of the engine to see, coarsely, like what's contributing to dropped frames. This is where you're probably going to spend most of your time optimizing. And again, if you target a 20% utilization, you can probably expect it to work on Quest, maybe iterate 10 times on the Rift and then deploy once to Quest. And depending on the settings you use when you package, you may be able to have a pretty short iteration time on the standalone target. But really, the Rift is instantaneous when you hit play, so that's a good place to do a lot of your work to be efficient. But once you're on the HMD, we also have the stat unit view rendering to a layer. So this is the perf layer that we offer, and it updates asynchronously to the rest of the iBuffer rendering, which means, as you're likely to be doing when you're dropping frames while optimizing, this will continue to respond to head tracking, and it'll be a more comfortable experience. And also, the same layer benefits that you get elsewhere apply here. You get sharp text, and it doesn't double sample it, so it's a pretty useful tool. It also bypasses fixed foveated rendering, so you don't have to worry about blurriness at the edges. But here's a close-up view of what that data looks like. You have graphs of different hardware resource utilization, and then you also have a prioritized list of areas of the engine that are costing time. So if UE4's built-in profiler doesn't give you enough information, for example, if you're competing with a background process for resources, or if you have thread contention issues for some reason, you can fire up Windows' excellent built-in event tracing system and look at the data there from a couple of different perspectives. And this is probably a workflow Rift developers know, but if you don't, I'd really suggest using this in your development process. So all you have to do, and we have documentation on this as well, is you run a script which installs our event manifests to make sense of the events once the trace is captured and initiates tracing. You run another script to stop the tracing, and then that trace that's dumped can be loaded in a couple of different tools that Microsoft provides. So the one that's shown here is called Windows Performance Analyzer, and it gives you a hierarchical view of all the system resource utilization, not just the one from the app you're profiling. But in this case, we've written a contrived app that just wastes a lot of GPU time. Actually, it looks like this is the CPU time case. But it's really just spin weighting, and that's showing up as a heavy spike in the right-hand side of the computation graph there. And you can also look at memory utilization. You can do snapshots before and after a certain event in your app. This will often let you zoom in on problem areas, like if there are phases of your program that are having problems. But it doesn't give you super detailed issues in terms of like thread contention or if there's something like going on with graphics driver behavior. So GPU view is another way you can load that same trace and view the information a different way. So when you first fire up GPU view, it's kind of information overload. And you generally want to look for areas where there are a lot of vertically stacked bars. So on the left there, we have some deeper queuing. And zoom in on that quickly. It lets you highlight a region and then snap to that. So here's a zoomed in view. The kind of behavior, the legend for GPU view is documented online, but there's kind of like these stacks of packets of work that occur in the system. So in a Windows system, there are packets on each hardware resource that get scheduled. So you can see when the packet got scheduled, how many are queued in front of it, and then what caused it. So in this case, we've selected a GPU packet, and it's highlighted both that and the CPU packets that spawned it. And we're looking at the metadata view here that tells us that it's a DMA packet, so it's copying data from one area to another. And in this case, we've got work for 2 frames stacked up, and there's a pink fence between them. So if you have vertex data that's causing a page fault, for example, you'll see that here. Lots of good information. Unfortunately, there is not a tool quite like GPU view available for standalone targets, namely Android-based ones. So systrace is an extremely useful tool there. In general, and who here has worked on Gear VR Go with systrace? OK, great. So relatively few. This is going to be a really useful tool for you as you transition from Rift to Quest. When you capture a systrace, you use the ADB command. You can dump an HTML file that you can then load up in your browser. And it has an interface sort of similar to GPU view with whole system utilization. This is going to be focused on the CPU utilization. It's not going to give you GPU details. And for that, you're going to need a different tool, which we'll talk about in a minute. But again, you can find the areas where there are a lot of, actually this time there'll be horizontal bars. And you can zoom in on those quickly. So here we have kind of a normal frame. And you can see the work on each core, and you can see the frequencies that the cores are running at. And you can also hover each of these bars and get more details. So in this case, like if like Linux scheduling is moving your thread to an unexpected core, you'll know that. Or if there's Wi-Fi driver or Bluetooth driver contending with your process, then you'll see that as well. So very useful tool for general system performance analysis. But you might want to know just kind of at a glance what's going on with your app. And actually, our VR API runtime provides that information in logcat. So ADB logcat is a command that you'll get to know and love working with Android. And you can filter with the VR API logcat filter to see a periodic performance report that we give. And it also can be information overload at first. But this is the ground truth for your app in situ. So like, there's no interposer, there's no like, invalidation of your use case. It's representative of how your app's going to perform for users. So let's see what that actually contains. So first is the frame rate. So in this case, the app is far below 72 hertz, and 47 definitely needs some optimization. It tells the prediction time. So when the app requests eye poses, those are predicted ahead to the time at which the runtime expects the user to see them. And in this case, the CPU code is running 45 milliseconds before we expect the final frame to be presented to the display, which is not terrible. We like to see things below 40 milliseconds, but that's probably not going to be a terrible experience. If you get above 50, it starts to get noticeable. How many frames are tearing? So this will increase if you're issuing if you have too many layers active, or if you're using the compositor too hard, if you have too high of an eye buffer resolution, for example. If the basically compositor is missing frames, then you'll start to see tearing. And this results in pretty significant artifacts for the user, so you generally want this to be 0. Early frames, again, is kind of due to the variability of the workload, especially that you're handing to the compositor. And stale frames are kind of your problem. These are how many frames you missed while rendering. And we noticed before that the app is running at 47 FPS, so we're expecting kind of a lot of stale frames here. vsync equals 1 is referring to the number of frames that we expect the app to synthesize per compositor frame, or vice versa, actually. We will, if this is 2, reproject every frame you give us twice. And if it's set to 3, if your frame rate is, if you're on the go, then you're expected to run at 20 frames per second instead of 60, which can, of course, cause significant judder. I don't necessarily recommend increasing that, except in maybe like video use cases or static geometry. And with, as Jian mentioned, positional error in play, this is usually not something you're going to want to set above 1 for Quest. Latency mode refers to software pipelining that you can enable or not. So if this is set to 0, it's kind of the shortest path from giving you the eye poses to presenting the display buffer. And if it's set that way, there are a lot of bubbles in the scheduling to get that low latency. May be appropriate for some sports titles, but generally I would recommend leaving this at 1. FOV actually is not referring to the FOV at all. It's the foveated rendering mode. So in this case, fixed foveated rendering is turned off. But the higher you set this number, the more aggressive the foveation setting is. We also tell you the current CPU and GPU levels. The 4 after the CPU just means that there are 4 cores available. And in this case, 2 and 3 is a little bit high. I would probably recommend trying to shoot for 1 or 2 in both. But that's a not uncommon setting. Again, the lower you set these, if you can get down to 0, 0, the longer your app will be able to run. And here are the actual clocks that the CPU and GPU are using as a result of those levels. And this can still vary due to our dynamic frequency and voltage scaling. So as Jian mentioned, we do dynamically vary the clock rates on both of those. And currently, it's optimized to minimize stalls, or minimize stale frames. So if you set your clock levels really low, and then you're still submitting too much work to make frame rate, we'll bump up the clock levels to help you deliver a comfortable experience, but you may still be burning a lot of battery. So you can watch the frequency there to see that. We also report the available memory. And the next one that's of interest is probably the temperature. If the temperature gets too high, it may mean that on average you're using too much memory, CPU or GPU. I mean, generally, below 37 is a good number. This app is particularly heavy, so I think, room temperature is a good thing to shoot for. But we've improved the ventilation substantially on our standalone headsets. So it's not like this is as big of a deal as it was on Gear VR. And this just reports the time warp GPU time. So in this case, there aren't too many layers active, and it's only taking under 2 milliseconds per frame. And then here's the total time, and in this case, 21 milliseconds is kind of what we would expect for 47 frames per second. So I mentioned that systrace will tell you all about CPU utilization and not GPU utilization. Well, unfortunately, it's hard to test your GPU utilization in detail in a representative setting. But Snapdragon Profiler does provide you with a lot of detail in a slightly modified setting. So this will give you all the performance counters on the GPU. It'll tell you all the operations that the GPU is doing. So if you're incurring a lot of resolves, for example, if you're doing blitz at the end of your frame to do HDR tone mapping or something, that'll show up here as a possibly huge performance cost. And so you just need to bear in mind that this is not doing front buffer rendering. The time warp is set up very differently here, and it's not quite the same, but the linear relationships between things will map to the end user's experience. So we often use this to detect grossly inefficient GPU utilization. But going back to the UE4 profiler and the VR API stats will get you a more representative view of what your user's actually seeing. There's also an excellent tool called RenderDoc that Nick mentioned. If you're using dump hitches, you can identify frames that should be investigated with RenderDoc and possibly with Snapdragon Profiler. RenderDoc generally operates above the GPU abstraction, so it's generally operating above the OpenGL-ES or Vulkan abstractions. But then you would use Snapdragon Profiler for below that and kind of what actual buffers and transfers am I causing here. So RenderDoc was covered in detail by Remy Palandri yesterday in the classroom, but soon you can check out the YouTube video of that. That's a very useful tool that I would highly recommend using. Snapdragon Profiler does also have this graph view of utilization over time. So there are a couple of different ways of looking at the data there. All right, well, thanks for bearing with us through all of that. We hope that you make amazing apps for Quest and that the transition from Rift is a smooth one. But it's not going to be easy, and I think that everyone in here has the power to make apps that are both as compelling as Rift apps and have the reach of a standalone target. So I'm excited to see what the future brings. Thank you.